Okay, still Sunday evening. I have another video for you. In this one, I want to address your questions about consistency-based alignments. Consistency-based methods for multiple sequence alignment. I realize that's a very confusing topic, and it's a challenging topic to wrap your head around. What does it mean to use consistency as a principle in building multiple sequence alignments? I've thought about this over the last few days. I've thought about how to illustrate the idea, and again, I've modified the slides, and this short video is going to try to walk through some of that illustration in hopes that it will be helpful for your understanding of this topic. So let's get started. Okay, here we have consistency-based methods. I'm going to skip some of these slides, the ones that we've covered in class and that don't have any, that aren't really directly relevant to the questions at hand. But there are some real questions, so let's get to it. Okay, so here we have our pair state HMM. The basic idea of an HMM is as discussed with the PET analogy, a hidden Markov model. In this case, we have a slightly modified hidden Markov model. A hidden Markov model in this case is not just giving us a sequence as we're going through the states. Each of these circles represents a state. But you'll notice that, for example, this one is giving us two sequences. It's giving us a position in our dynamic programming matrix. And so the path of our dynamic programming, we can begin here at the upper left and we end at the lower right. And our alignment is going to be basically going from the beginning either to an insertion on one, an insertion on the other, a match, and then say if it keeps matching along the diagonal, we're just going to continue here going through this and then eventually to the end. Or if there's an insertion on one strand here, it would go to here and then pop back when it gets back to a match, similarly on the other strand. And each one of these has a little probability that's associated with it, and ultimately the optimal alignment is going to be the path that gives us the highest probability. That's the idea. Now, the idea of consistency is we start by considering two sequences. We're going to use X and Y through this whole thing, and we consider a position I in sequence X and a position J in sequence Y. If those positions are aligned, when we're considering that possibility, we can describe that as X sub I tilde Y sub J. Now, if we're going to consider a third sequence, we can also look at X sub I and its alignments to positions in Z, and we consider Y sub K and its alignments to position in Z. So this is the formal idea of consistency at a very high level. If X sub I, that position, is aligned with Z sub K, and Z sub K is aligned with Y sub J, then that should influence us. That should say that X sub I should align with Y sub J. That's the basic idea. Things should be consistent. Now, how it's used is in this formula, and I am repeating this, but I do think it's worth repeating. We have basically, when we're doing a pairwise alignment, it's kind of like this. We have a probability of these two being aligned given the sequences. And that's how we can represent that in that pair state HMM. So that's the ordinary pairwise alignment as a conditional probability. That would be what appears in the pair state hidden Markov model. But if we're incorporating information about a new sequence, sequence Z, where it aligns with positions X sub I and Y sub J, we're going to get something new. So the thing we get that's new, notice here, this, when I say conditional probability, there's a probability of these two residues being aligned given what's on the right, X and Y. But now we're adding something to the right, given X, Y, and Z. We haven't changed anything on the left. We're still asking only questions about X sub I being aligned at Y sub J. The way these conditional probabilities work, we can assume with some pretty straightforward assumptions, what we can do is basically sum, since we're adding this position, this sequence Z, we can basically sum over all the positions in Z, so from 1 to K, and look at that alignment with X sub I and that alignment with Y sub J, those two conditional probabilities. We sum the product of those over all K, and that becomes our conditional probability given X, Y, and Z. So that allows us to consider this third sequence Z. Okay, so far I haven't said anything new. I've just repeated myself from the more confusing aspects of class. This is what ProbCons does. So ProbCons uses this pair state HMM, which is what is up here, and then computes the accuracy and then uses some information about conservation. Now, let's skip forward here through these examples. And now what I've done is I've come up with two kind of visualizations of this, of how to consider it. And I'm trying to use some examples. I think these are pretty useful, but if you don't like the first one, the second one may be better. So here's the first one. We have here a sequence X, which is MDKT, and we have a sequence Y, MQKT. You can see they only differ at this second position between an aspartate and a glutamine. Everywhere else, they're perfectly matched. And in particular, the aspartate glutamine, the DQ in blow sum, is weak. It is weak. It has a score of 0. When we turn that into a probability, that's at position 2, so it's X sub 2 against Y sub 2. That probability is just based on XY comparison alone, and that probability, this position contribution to that probability is not going to be high. It's not going to be any different from random chance. Now, if we add a third sequence Z, and we compare it to X, now Z is going to be MEKT, so this is going to be a glutamate. So now we're comparing an aspartate to a glutamate. That has a position, that has a score in blow sum of 2. So this position here, X sub 2 aligned with Z sub 2, has a score of 2. And if we were to turn that into probabilities, the probability that X sub 2 is aligned with Z sub 2 given X and Z is based on XZ comparison alone, but this position is going to contribute more to it because the score is higher. In progressive alignment, all of this would all happen in progressive alignment when we're constructing the guide tree. Now we can consider Y and Z. So Y and Z is now going to be at position 2. We're now comparing Q and E, so a glutamate to a glutamine, and that also has a score of 2. So this is going to be the score here, and the probability based on Y and Z, YZ comparison alone, that position within that probability is going to be making a greater contribution. The difference, what we get when we use the idea of consistency is we get to use this information here and this contribution, this positional contribution to that alignment, and this positional contribution to this alignment to alter the probabilities that we estimate for this position. And it works like this. So we say, okay, D versus Q, which is our XY comparison, is weak and has a score of 0, so that position doesn't contribute so much in terms of probability. But this position has a stronger score, contributes a little more to that alignment. This position has a stronger score, it contributes a little more to that alignment in terms of probability. And when we incorporate that into a consistency-based alignment, we get to basically use this indirect information, that this alignment in here and this alignment in here get to contribute to our interpretation of what should happen at position 2 when we're aligning X and Y. And what we end up getting is basically this. We get this thing here. So position here is now the sum of the products of these probabilities. Now, if you just look at x sub I z sub k for xz, just at position 2, that we already know that's going to be higher. The score is 2. And just this position is going to be higher because it has a score of 2. So those two, which are at position 2, 2 and position 2, 2, those are telling us that they're going to influence the this conditional probability of x sub I, y sub j, and they will make it stronger than it would have been if we were just considering the pairwise alignment. That's the idea of consistency. Now, if you don't like this visualization, and you might not, I thought of another one. So here's my other one. This is a little higher level, but I think it is also useful to think about. Here's, in progressive multiple sequence alignment, we build a guide tree, as we have said many, many times. We build a guide tree based on the pairwise sequence comparisons. These are all the pairwise sequence comparisons between x, y, and z. And looking at each of the arrows here, each of these double-headed arrows represents a pairwise comparison, and it kind of looks like they're connected, right? Because they involve shared sequences. But they're not actually connected when you're doing progressive alignment. In reality, it's not like this. In reality, it's more like, well, when you're comparing x and y to build the guide tree and Clustal, you don't incorporate any information about z. You're just looking at the comparison between x and y. When you're comparing x and z, you just do that comparison. You're not looking at any information using sequence y, despite the fact that obviously when all the arrows were drawn, they were connected. And when you're looking at z and y, you're not looking at anything from sequence x. That's how progressive alignment works. That's how Clustal works. It builds the guide tree based on the pairwise comparisons alone, even though we can tell from that first one that they're connected. In a consistency-based alignment, we do something a little different. When we're comparing x and y, and I don't go through all of these, when we're comparing x and y like this, we have this pairwise comparison between x and y, but we allow z to influence our interpretation of x and y. We allow z to do it by virtue of the alignment between x and z, and by virtue of the alignment between y and z. That's the requirement for consistency. Everything should be self-consistent in this. And again, it winds up giving us this formula here for the conditional probability given this additional sequence z as the sum of the products of the conditional probabilities across the positions in z for that position in x, those positions in x and y. So we support the alignment of x and y not just by x and y alone, but by adding up all this matching indirect evidence along all the positions in our sequence z. Okay, that's the basic idea. I'm going to end with one more thing because we've gone through these 3 different classes of multiple sequence alignment methods, and I want to just use a little bit of a chance to round up and compare them. So we have these different methods, and to reiterate the ideas, in progressive alignment, of course, we're going to build the alignment, the multiple sequence alignment step by step. Critically, we build the guide tree by only doing pairwise comparisons, and then we follow that guide tree religiously. So it doesn't allow us to go back, doesn't allow us to look at the choices that we made, it doesn't allow us to consider any repositioning of gaps. In iterative-based alignment, what we're doing is we're still not looking at that indirect evidence up front, but we are allowing ourselves to do realignment by breaking apart the sequences, breaking apart the multiple sequence alignment in ways that were not explored in the original construction, realigning, and then using that as a way of kind of polishing the fit of our data to our model, and or our model to our data. And we use that to iteratively, again and again and again, and polish it in order to improve the fit of our data and stop when we basically don't get any better. In consistency-based methods, the difference is that we're using that third-party evidence, and in particular, we're using it up front. And we can, again, use this analogy of like a friend click. If we don't know somebody, but we are introduced to somebody and they are already a friend of a friend, then we might be more inclined to be interested in their friendship. So here it's basically we're using that indirect evidence to weight our trust in the alignments that we would otherwise be looking at just in complete isolation. So that's the idea of consistency. Those are a couple of attempts, however flawed, to kind of illustrate the ideas of consistency-based alignments without getting too deeply into the mathematics. And I hope that even some of the mathematics that is there makes some sense in terms of I don't want this. It shouldn't be intimidating. It's just math is just a language, right? So it's there, but also I think some of these analogies and visualizations help to make sense of how the principles get manifest in those equations. Anyway, that's it, and I will see you all in class.